Welcome everyone. We, Saira Prasad, Heba Syed, and Lita Wong are proud to present A Life in Color, a 2B production. Why did we decide to talk about color today? Well, color is one of the things most of us take for granted in our lives. It's omnipresent, yet we rarely wonder where it comes from. Our goal today is to analyze a few of the various chemical origins of colors in our lives and their potential effects and usages.
Our experiences with color begin with how we perceive it. What is color and how do we process color? If you read the quote by abstract painter Hans Hofmann, you know that color is light or photons of certain wavelengths. When light strikes an object, incident photons are emitted at a certain color and, upon contact with an object, can end up in three places. They can either be absorbed, reflected, or transmitted. These wavelengths enter our eyeballs through our pupils. The ones that also fall in our visible spectrum, 430 to 770 nanometers, are the ones we actually perceive. At the back of our eyeballs is a layer called the retina. This layer is filled with photoreceptors, each of which is excited by a specific wavelength of light. We have rods, which perceive black and white, and we have cones, which perceive color. When light hits the photoreceptors, it excites the photoreceptor and induces something called photocycle formation, which is basically a series of conformational changes inside. This triggers an impulse or action potential by opening sodium channels and flooding neurons with sodium ions, creating a potential difference. These impulses travel through neurons by jumping between nodes in the myelin sheath, the insulating substance that coats the axon or the length of the neuron. To summarize, light striking a photoreceptor triggers a signal transduction pathway in which photoreceptor excitation leads to photocycle formation, which leads to a potential difference and firing in our neurons. The chemistry of photocycle formation is depicted in the following. When light hits the photoreceptors, it excites the valence electrons in alkenes, organic molecules with carbon-carbon double bonds, to a higher energy level. As you can see here, according to molecular orbital theory, one of the valence electrons transitions from the bonding pi orbital to an anti-bonding orbital, which destabilizes the pi bond. Using ethene as a model for the carbon-carbon double bond, we see that stable pi bonds hinder rotation due to degenerate p orbital overlap. When the pi bond is destabilized, rotation can occur around the carbon-carbon axis. This phenomenon causes the isomerization of a component of rhodopsin called 11-cis-retinal to all-trans-retinal. In the cis configuration, these two groups are on the same side of the pi bond, which kinks the chain, whereas in the all-trans configuration, the groups are on opposite sides and the chain is straight. This is the conformational change that triggers the signal transduction pathway mentioned previously. Now that we know how we perceive color, let's discuss how we are able to perceive different colors which are formed from a few primary colors. There are two models to explain how color is mixed, the additive and the subtractive model. The additive model, also called the RGB model, refers to light being emitted, for example, by electronics and TV screens. Color is additive because you add up whatever wavelengths are being emitted. Mixing the three primary colors, red, green, and blue, creates white light. Mixing two colors gives the results shown. For the subtractive colors, we use the CMYK model, K being the key color or black, and the others being cyan, magenta, and yellow. This is what we use for pigments when we're printing pictures or dyeing cloth, because light is being absorbed and reflected rather than emitted. Thus, when you mix two colors, you subtract the wavelengths absorbed with the results shown above. So when you mix yellow and magenta, you're absorbing green and blue and are left with red light. Interestingly, the additive primary colors mix to form the subtractive primary colors, and vice versa. CMYK, RGB. Now that we've covered the foundations of what is color and how we perceive it, we'll be discussing the origins of colors in our lives. Three in particular: elements, inorganic compounds, and naturally sourced. Let's start with the chemistry of colors on an elementary level. So here's the spectrum of visible light and the absorption spectra of sodium, mercury, and lithium respectively. When light is absorbed, the valence electrons in elements move to a higher energy level, and these absorption spectra show which wavelengths of light are absorbed by each element. Conversely, here are the emission spectra of the elements. These are caused by valence electrons falling from a higher energy state to a lower one, which releases energy as light, causing particular wavelengths to be emitted. Here we show the emission levels of hydrogen as an example of what we mean. Building off this concept of electrons rising or falling in energy levels, we get to band theory. When atoms combine to form substances, the outermost orbitals merge, which provides a greater number of available energy levels for electrons to assume. When a large number of atoms are close to each other, these available energy levels may form a band. Overlaps between these bands allow electrons to drift freely through different energy levels. More overlap means a decrease in the gap between energy levels. Wide gaps mean that a substance appears black because it absorbs all wavelengths, whereas small band gaps appear white because they don't absorb. Semiconductors and insulators often have a gap between bands, whereas metals have nearly continuous bands. This enables them to reflect light because light waves can cause free electrons in the metal to oscillate. Metals have color because of their reflectivity at different wavelengths. For example, gold and copper have low reflectivity at short wavelengths, so yellow and red are reflected. Silver has good reflectivity that does not vary with wavelength and therefore appears close to white. Himalayan pink salt gets its color from trace minerals such as calcium, potassium, magnesium, and possibly iron oxide.
We will now discuss inorganic compounds. Let's start with gases. As I'm sure most of you are well aware, almost all gases are virtually colorless. However, the heavier halogens have more prominently colored vapors as you go down the group. This is in part because you can predict the color of a gas based on its chemical properties, namely how polarizable its electron cloud is. Most gases, however, can cause us to perceive color. Rayleigh scattering is the scattering of light by particles in a medium without affecting wavelength. However, we perceive a different color because light waves are scattered upon contact with particles. This explains the blue color of the sky. We'll next touch on the colors of transition metal ions, so why Rust is orange or the Statue of Liberty is green. We know that electrons in an atom are arranged in different shells which have subshells called orbitals like s, p, d, and f. Transition metals are unique in that they contain partially filled d orbitals, which are key to the color compounds and complexes they form. Complexes are formed where transition metals bind to one or more neutral or negatively charged non-metal species, or ligands. This changes the metal's d orbitals from degenerate to being at different energy levels. Due to differing shapes, some d orbitals are closer to the ligand than others. Electrons flow from lower energy to higher energy d orbitals by absorbing light. Any unabsorbed wavelength or light are transmitted, causing the colored appearance of the compounds. Finally, we'll talk about naturally sourced colors. The vast majority of naturally sourced colors are organic compounds. As a review, organic compounds are usually comprised of a hydrocarbon structure, which may have simple or complex functional groups. The simplicity or complexity of these groups is what gives these compounds colors. The simpler the functional group, the less color the molecule has. Take glucose, for example, which only has an OH group and it appears white. The compound pauline has different colors depending on how it interacts with different solvents. In the case of pauline, the majority of color comes from its structural conjugation. Conjugation is an alternating double and single pi bond arrangement. Here we show the difference between conjugated pi bonds and an isolated pi bond. Because of the conjugated arrangement, these pi bonds can experience resonance and the electrons can be delocalized over this whole region. Molecules with conjugated systems of electrons have small energy gaps than non-conjugated systems, so low energy light is absorbed by conjugated systems. How does this process result in apparent color? Well, the energy of the various colors in the visible spectrum is different depending upon the color. The energy of visible light increases from red to violet. A highly conjugated system, for example, might absorb the lower energy portion of the light and reflect what is not absorbed, which is what we perceive. Basically, the color reflected is the complementary color of the color absorbed. For example, if a violet portion of the spectrum is absorbed, the complementary color of yellow is what is observed. Plants are a main place of naturally sourced colors. Their color originates mainly from four compounds: carotenoids, which are deep red, yellow, or orange in color; chlorophyll, which is found in all green plants; anthocyanins, which are pH dependent but naturally deep blue or purple; and turmeric, which is also pH dependent but naturally a deep yellow.
Anthocyanins. Carotenoids. Baby carotenoids. Look at all that chlorophyll.
Melanin is a pigment found in animals. The two types that give color to skin and hair are eumelanin and pheomelanin. The production of melanin starts with the amino acid L-tyrosine. The enzyme tyrosine hydroxylase converts tyrosine into an oxidized dopa molecule, L-dopa. Then the enzyme tyrosinase catalyzes oxidation of L-dopa to the reactive intermediate dopaquinone, which is polymerized to make melanin oligomers. Skin and hair color indicates what type of melanin is most prominent in a person. People with dark skin and hair have lots of eumelanin, people with red hair have lots of pheomelanin. If you're watching this from a screen, wavelengths of red, blue, and green light are being added to create the variety of colors you see. When the light strikes an element, photons are absorbed, exciting electrons to a higher energy level. When these electrons fall to a ground energy level, photons are emitted. Absorption spectra show us which wavelengths are absorbed, and emission spectra show which are emitted. Band theory describes how valence orbitals combine to allow electrons to drift freely between them. The colors of organic compounds are determined by the simplicity or complexity of their functional groups, as well as the degree of conjugation or alternating double and single bond arrangements. The color of light reflected is often complementary to the color of light absorbed. In plants, color originates from carotenoids, chlorophyll, anthocyanins, and turmeric, while in animals, melanin acts as an important pigment for skin and hair. So as the sun sets on our presentation, we want you to remember that light is the source of color, whether that light is reflected or emitted. It's a delicate chemistry within our photoreceptors that allows us to perceive color. These colors come from wavelengths absorbed, reflected, and emitted by elements, as well as the electron transition of both organic and inorganic compounds. Thus, we are able to enjoy the colors around us that give light to our lives.